Welcome back, everyone. My name is Zach Barnes, and in this video, I'll be reviewing what we went over in the past video about continuity and going into how we can find if a function is continuous algebraically and finding continuity at a single point. So if you remember from last video, we went over what continuity is and defining it, and we know that continuity is when a function is able to be traced with a single line with no breaks in it. As you see here, this function's traced nice and smoothly with no jumps or any kind of vertical asymptotes interrupting it. And our three forms of discontinuity were removable, jump, and infinite discontinuity. And so going forward, what we'll be talking about today is really continuity at a particular point. And so when we want to find if a function is continuous at a particular point, we have to look at three main things really, and that would be we have to look at the limit from the left side, the right side, and f of a or f of a number to see if that's truly a solid dot, a solid circle or not. So, as we can see here with this absolute value graph, if we look at the limit coming from the left, we see that as it moves from left to right, we slowly approach 2, right? And when we look at the limit from the right, it slowly approaches 2 as well, okay? And then when we look at f of 2 itself, we see that it is equal to what we have for the limit coming from the left and from the limit coming to the right. So when the limit of x approaches 2 from the left, we see that it is equal to 3. And when we look at the limit of x approaches 2 from the right, we see it's also equal to 3. And then, as we just went over now, f of 2 is also equal to 3. So we know that this absolute value is continuous at x equals 2. Here we have a really good example that I like to use for finding continuity at a particular point. And our question in this problem is this function continuous at x equals 1, x equals 2, and x equals 3? So the first thing we look at is x equals 1 here. So the first thing you have to do is test the limit as x approaches 1 from the left, meaning from left to right. What does that equal? So we see here in the graph, as we move from left to right on the graph, our function gets closer and closer to 1, okay? And then when we test the limit as x approaches 1 from the right, we see the same thing. We come here from infinity, and then our function gets closer and closer to 1. Now, when we test f of 1, we see that there's an open circle here, and then a closed circle up here where it's equal to 3. So that means that f of 1 is equal to 3. And this means that we have jump discontinuity, because look at this gap between here, right? We have a closed circle up here and an open circle up here. So we are not continuous at x equals 1. Looking at x equals 2, we have to test the limit as x approaches 2 from the left. So as we move from left to right, we see that our function approaches infinity as marked by these arrows here. So we can say that the limit of x approaches 2 from the left is equal to positive infinity because it goes on forever and ever. When we look towards the limit of x equals, or as x approaches 2 from the right, we see the same thing. Moving from right to left, our function is slowly approaching infinity as marked by the arrows here. So we say that the limit as x approaches 2 from the right is equal to positive infinity as well. Then the final test is f of 2. So here, since we have a vertical asymptote at x equals 2, we could say that it's undefined, meaning that this, at x equals 2, this function is not continuous at all, because we have infinite discontinuity, for it goes on forever and ever. Now the final test, we have x equals 3, so we must test the limit as x approaches 3 from the left, and we see in our graph here, as we move from left to right, our function slowly approaches 1. And then, going forward, when we test the limit as x approaches 3 from the right, we see from right to left, our graph is slowly approaching 1 as well. Then, finally, as we look towards f of 3, we see that there's a closed circle at x equals 3 at 1. So, we know that this, at the value x equals 3, we know that our function is continuous. Here we have a really good example of trying to solve continuity using algebra. And our question here is whether or not g of x equals 2x squared plus x minus 6 all over x minus 2, if that's continuous. So the first thing we must do is see if this function is undefined anywhere. And we see that when x is equal to negative 2, which will turn the entire function into something over 0, that will turn it into an undefined function. So after we find this, we can go on and factor the numerator, which will go on to help us later when we try to factor out our numerator and denominator. So we take 2x squared plus x minus 6, and we can use slide and divide by multiplying the 2 by the negative 6, and we now have x squared plus x minus 12. And this we can then factor into x plus 4 and x plus 4 and then x minus 3. However, we must account for the 2 that we did multiply earlier on. And now we have x plus 2 and 2x minus 3. So once we've done this, we can go on to solve our limits. And so we have limit of x as it approaches negative 2. Now remember, we said that our function is undefined at negative 2, so that's where we get this limit as x approaches negative 2. We see, now we do the limit of x approaches negative 2 from the left first with our newly factored numerator. And so we can cancel out like terms here, x plus 2, x minus 2, these cancel. And now we have 2x minus 3. And if you learned before, when you try to solve limits, you can use direct substitution. And so that will then get you your answer of negative 7. And then next, you can go on and solve the next limit of the limit of x as it approaches negative 2 from the right. Same process, we cancel out like terms here, and we have the same answer here. We can use direct substitution, which will then give us our answer of negative 7. So, as we said before, when we try to find f of negative 2, we know that this does not exist, since that is what makes it undefined. This is what makes our numerator of the original problem of g of x, that makes that undefined. And so we determine that our function here is not continuous, and we have removable discontinuity at x is equal to 2.